Greetings, Internet Scholars. This is your Jesse Stiles. Welcome to a very special episode of Twisted Signals. Today we are going to be looking at signals in the frequency domain. And specifically, we're going to be looking at how we can represent complex signals by breaking them down into a bunch of individual sine waves. This idea is known as representing a complex signal with the Fourier series, and it's named after this guy, Joseph Fourier. Joseph Fourier was a 18th century French mathematician physician who came upon this concept in his studies of heat and vibrations, that any periodic signal could be described by sine waves that are related to that signal. So we're going to look at how you do this. So let's look at signals in the time domain and the frequency domain side by side. And we're going to start with a sine wave, because the sine wave is the sort of atomic building block of signals. It's the simplest possible signal. It's just this sinusoid that's going to be repeating itself at some frequency. It has a certain amplitude, which is its displacement from the x-axis. And the phase of this sine wave is going to be changing depending on where we are within its repeating cyclical waveform. So when we look at a signal like this in the time domain, this is what we traditionally call an oscilloscope. The y-axis is the amplitude of this signal, and the x-axis is time. So as we move forward in time, we're seeing that amplitude change. Next to this, we are looking at a different view of this signal. We're looking at it in the frequency domain. And in this view, our x-axis is frequencies. So we have on the left side of this graph low frequencies, and on the right side of the graph high frequencies. And you can see our domain is described here, where it's going to be between 0 and 22,000. So if we were to increase the frequency of this sine wave, in the time domain, you can see that this signal is now repeating itself more frequently. And in the frequency domain, you can see that the level of energy has shifted to the right, showing us that we have energy higher in the frequency spectrum. Now, this domain is going to be determined, of course, by our sampling rate. So our sampling rate is 44,100. And that means we can represent signals up to 1/2 of this sampling rate accurately. So 1/2 of this would be 22,050 cycles per second. So a plot like this is going to make sense with this sampling rate. And these frequency ranges are, of course, because this is a representation of an audio signal, the boundaries here are determined by the range of human hearing, where around 20,000 cycles per second is the highest frequency that human beings can hear. So this is going to be a range that covers the entirety of human hearing. Let's look at a more complex signal. I'm going to switch this generator to show me a square wave. And let's bring down the frequency. Okay, so in the time domain, you can see that the shape of this waveform has changed into this blocky rectangular shape. We can hear a pretty obvious difference in sound quality. So this has the same frequency as the sine wave, but it's a much brighter sound. So it has all these harmonics that make it a brighter, richer sound with a different kind of timbre. And in the frequency domain, we can see where that brightness comes from. Let's look at the sine wave and the square wave. And when we look specifically at the frequency domain representation, we can see the two signals have the same big peak. This is the fundamental frequency of this signal. But the square wave has all these other little peaks that kind of trail off as we move upwards in the frequency domain. So let's look at what exactly these are when we are considering a square wave. In this exercise, we are going to attempt to build a square wave from scratch using just sinusoids, where we are going to very specifically set the frequency, phase, and amplitude of each sinusoidal component of this complex signal. So let's start off by listening to a regular old square wave as generated by FFTs, which is the built-in rectangular waveform generator that comes in Max. So the frequency is 100 cycles per second. We're looking at it in the time domain, and let's listen to it. We've got this bright, buzzy sound. And this switch here is going to switch to this. This is going to be our reconstruction made out of sine waves. So cycle tilde is our sine wave generator, and I'm attenuating this by doing some division at audio rate. I'm dividing by 1, which gives us, of course, the same values. And so we're taking the output of that and we are graphing it in the time domain, and we are using send and receive to listen to it. So you can hear that this sine wave has the same fundamental frequency as the square wave. So they are both repeating themselves at the same rate. But the square wave is much brighter because it has all these harmonics. Harmonics is this term that comes from music, where a harmonic is going to be an integer multiple of the fundamental frequency. So if our fundamental frequency is 100 cycles per second, as it is here, the harmonics would be 200, 300, 400, 500, and so forth. That's known as the harmonic series. Now, I happen to know that a square wave only contains the odd numbered harmonic of some signal. So if our fundamental frequency is 100, the only harmonics that are going to be in a square wave are going to be 300, 500, 700, 900, and so forth. So we're going to reconstruct the square wave using just those odd numbered harmonics. So 300 and 500 and 700 and so forth. We would have to continue sort of infinitely. I also happen to know that every other harmonic in a square wave is out of phase. So the second argument we can give to cycle tilde is the phase, and it's in this range of 0 to 1. So I'm making every second harmonic out of phase with the previous one. And then finally, I happen to know that every harmonic in a square wave is going to be attenuated by a very specific value, which is just going to be dividing by the number of that harmonic. So for the third harmonic, I will divide by 3. For the fifth harmonic, I'll divide by 5. The seventh, we divide by 7, and so forth. So let's just start adding these components in. I'll connect it to the visualizer and we will listen to it. So it's a little bit brighter and the shape is a little bit more similar to a square wave. So as you can see, with every harmonic we add, the shape and the sound of this waveform is getting more and more similar to our target, the square wave. So if we continue doing this infinitely, we would be able to perfectly recreate this square wave, as Joseph Fourier has proven. And to simplify the work here, here's a demonstration of this concept using Polytilda. So Polytilda, we looked at this during one of our in-class exercises. This is a system where we can make multiple instances of some base patch. So if we double-click Polytilda, you can see my base patch. And it's using this Polytilda to report the instance number. And then it does some math using EXPR to set the frequency, the phase, and the attenuation value of many different sine waves. So let's tell Polytilda that we want 3 copies of this base patch. And so it's loading 3 instantiations of my base patch, and we can look at them by saying open 1. And here's our first instance. So it does the math, and it creates a sine wave with a frequency of 100, a phase of 0, and this attenuation value 1. The second instance of my patch is going to create the odd numbered harmonics. So here's harmonic 3. The frequency is 300, the phase is offset, and the attenuation value is this, 3. And then the next instance, we'll just continue going up through the odd numbered harmonics, offsetting the phase for each one, and then attenuating by the harmonic number. So if we loaded, let's say, 50 copies of this patch, we have 50 harmonics, and this sounds quite a bit like the original square wave at this point. Let's try 100. So with 100 instances of this patch, it's starting to sound pretty indistinguishable from the original. And we could open, here's instance 77, and we're seeing this is the 77th harmonic inside our synthesized square wave. So because I happen to know the specific values for all of the frequencies, amplitudes, and phases of the harmonics in a square wave, we can perfectly reconstruct this signal by hand using individual sine waves. While we're at it, I just want to record a quick test signal that is going to be useful later on in this lecture. I'm going to copy out this chunk of code and make a new patch. Okay. Let's listen to 3 copies of my bass patch, and let's set the bass frequency to 86.1. And I'm going to record just a couple seconds of this signal, and this is going to be useful to us later on in the lecture. So to make a quick recording, I'm just going to go to Extras, Quick Record. I'm going to specify the file name and the place where I want to record it. So let's just put it here, and I'll call it 86.1. And let's just record a couple seconds. Okay, great. Thanks, Max. Close that, don't save it, and we can go back to our lecture. So this is the basic idea of the Fourier series, that any complex periodic signal can be broken down into individual sinusoidal components, each of which is going to have a specific frequency, amplitude, and phase. And if we can specifically describe all of those sinusoidal components, we can perfectly reconstruct our signals. With this understanding, you can look at many different examples of this concept in science as well as art. So there's some links that you can see underneath this video to other things on YouTube that demonstrate this idea. This is a lecture in which somebody's going to reconstruct a saxophone sound out of individual sine waves. This is a really beautiful visualization of the Fourier transform to help us better understand the math underlying it. And we have a really interesting piece of installation sound art by Tristan Parrish called Microtonal Wall. This piece is one in which the artist is creating the sonic experience of noise using many different tone generators, each of which is tuned to a different frequency. So noise is a completely random signal. Let's just look at noise in the frequency domain. So here, noise tilde is our random signal generator, and here's a spectroscope. And let's just turn on audio in this window. So you can see that noise has equal energy everywhere in the frequency domain. So go watch this video. You'll see the artist create what sounds like noise from a distance, but as you approach the sculpture, which is comprised of lots and lots of different loudspeakers, you see that each loudspeaker is actually emitting a really specific fixed frequency. Just these frequencies are distributed across the spectrum. So when you add them all together, you get this experience of noise where it's equal energy throughout the frequency spectrum. And we also have a demonstration of this idea in this subpatcher from our lecture here. So here we're using Polytilda. This time we're going to use Polytilda to reconstruct noise using random sine waves. So let's start off by listening to real noise from our noise generator. So here's our base patch. We're going to use the instance number to spread these instances across the spectrum, and we're going to randomize those frequencies somewhat. So we've got just one voice here. Let's listen to that one voice. So that's just this one sine wave. Let's make more voices. Here are 70 voices. Here are 200 voices. Here are 200 voices. Here are 400 voices. So as we add more and more voices, we are getting closer and closer to the sound of noise. For it to really sound like noise, we would need just a ton of oscillators throughout the whole spectrum. And in this piece, Microtonal Wall, the artist has done pretty much just that, and he's done it in the form of a sculpture, which is a pretty interesting demonstration of creating a complex signal out of many simple components as a sculpture. So to determine the spectral components of a signal, we use an algorithm known as the FFT, the fast Fourier transform. The FFT can take a complex signal and calculate out all of the individual spectral components of that signal, and it can give you the information about the frequency, phase, and amplitude of all of those different harmonic components of the signal in the frequency domain. So let's look at some examples of the FFT in Max. So a simple way to do an FFT in Max is this object, FFT tilde. FFT tilde is going to analyze a signal in the frequency domain and give us information about the amplitude, phase, and frequency of many different frequency components. Those frequency components are sometimes called bins. So we're going to take the spectrum of frequencies and divide them up into bins. And for each bin, we're going to figure out the amplitude and phase of the signal that's in that specific frequency bin. These frequency bins are all going to be integer multiples of some base frequency. So you can kind of think about this in musical terms. You can say your FFT has a fundamental frequency, and then there's all these integer multiples of that fundamental frequency where we're going to be looking at the signal and getting the information that's there. So at the top of our patch, we are calculating the fundamental frequency of our FFT by looking at the sampling rate and then dividing it by the size of the FFT in terms of samples. We'll explain this a little bit more later in this lecture, but that gives us this value, 86.1. This is the fundamental frequency of our FFT when the sampling rate is this, 44,100, and the size of the FFT is 512 samples. I'm taking that base frequency of the FFT, I'm multiplying it by 10, and we're going to use that to set the frequency of two different oscillators. I've got a square wave and a sine wave. So let's start off by looking at the sine wave. So you can hear we've got this kind of high frequency sine wave. And I'm going to take the 3 outputs from FFT, and I'm going to use this object capture tilde so that we can look at the audio signal as a list of floating point numbers. So I'll say clear, and then I can double click on capture tilde, and we can see what we have captured. So you see a bunch of numbers. Most of them are 0, with the exception right here, we have this large non-zero value. It's 256. And let's look at where that is in the list. And we're going to count starting from 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the 10th position in this list. And remember here, we're multiplying by 10 from the fundamental frequency of our FFT. So in this 10th harmonic of the FFT, we see this large non-zero value. Let's look at this one. So here, this is just zeros everywhere. Interesting. And let's look at this third one. This one seems to be a list that's going up by 1 for every value. And it's going to go up to 511 and then wrap around again. So this one is just a list that tells us the frequency bin that is being captured at that instant in the signal. So we have bin 0, bin 1, bin 2, bin 3. So these other values, we can kind of figure out what part of the signal they are by looking at this. So that non-zero value was at position 10, frequency bin 10, and we know that it's going to be the 10th multiple of this, the fundamental frequency of our FFT. All right, let's try it again. This time we're going to use the square wave. I'm going to wait for this motorcycle to drive down my street. Okay, and let's turn on audio. So, same sound, but now it's a square wave. Let's hit clear. Looking at what I've captured this time, I have, again, a bunch of zeros, and then at the 10th harmonic of the FFT, I have some non-zero value, but wait, there's more. As I keep going up through the spectrum, we've got more zeros, but then when we get to the 30th position in the list, we again have a non-zero value, and then at the 50th and the 70th and so forth. So these are those odd numbered harmonics that we know we're going to find inside a square wave. Let's look at the second capture. Kind of the same deal here. We've got a bunch of zeros, and then we get to the 10th harmonic and the 30th and the 50th and the 70th, and we see the energy inside the signal at these specific positions in the spectrum. So what are these numbers that we're getting from these two outlets, the first two outlets of FFT? If we hover our mouse over it, we see it's the real output and the imaginary output. What the F does that mean? The third one is the ramp that tells us the frequency bin number, but real and imaginary. In math, we can represent a position in two-dimensional space using a complex number. A complex number is a pair of two other numbers that we think of as the real and the imaginary components of this complex number, where the real number is the x-axis and the imaginary number is the y-axis. So by combining a real and imaginary number, we can specify some position like this. And when we're talking about the FFT and we're using this position in two-dimensional space to describe a frequency bin, what we're describing is the amplitude of the signal at that place in the spectrum and the phase of that signal. So the amplitude is going to be the displacement from 0, 0, and the phase is going to be how far along the unit circle we have moved. So these two signals combined describe the amplitude and the phase of that signal. Now, we might want to actually directly understand the amplitude and the phase to do useful things to the spectrum. So to convert the complex real imaginary numbers into amplitudes and phases, we can use an object called car-to-pole, and that stands for Cartesian to polar coordinates. So Cartesian to polar coordinates takes the Cartesian coordinates. Cartesian coordinates are going to be the real and imaginary numbers. And then the output is the amplitude and the angle. So you can see anywhere where we're displaced from 0, 0, we have a high amplitude, and what we're changing as we move around is the angle. So we're going from 0 to pi, and then minus pi back to 0 as we move around this way. So that's like the amplitude and the phase. And we can convert them back into Cartesian coordinates using pole to car, which stands for polar to Cartesian. So let's do an FFT again, but this time we're going to take our audio rate, real and imaginary signals, and we're going to run them through this object, car to Polytilda. And this is going to, at audio rate, convert these into polar data, and the output is going to be the amplitude and the phase. So this is going to be a little more understandable when we run audio through it and when we look at the results this way. Let's look at this. Okay, I've got square waves and I've got noise. And this time I am going to set the frequency of my square wave just directly to this. So 86.1 is the fundamental frequency of my FFT. I'm just multiplying by 1, and I'm using that to set the frequency of this square wave. So let's turn on audio. Let's clear these captures, and let's look at what we got. Okay, so this is bin 1. This is going to be the fundamental frequency of the FFT, and we can see we've got a lot of energy right there because the square wave has the same fundamental frequency. This is bin 2. We know that square waves don't have energy at the even numbered harmonics, but here we are at the first odd numbered harmonic, and then the next one and the next one. So we can see we have amplitude values at all these odd numbered harmonics, and we can see that they're starting to fall down to lower and lower values as we move up and up throughout the spectrum until they get really close to 0. So this is the amplitude information about this square wave. And then this is going to be our phase information. So here we can see these phase values as we look at all the different odd numbered harmonics. And then our third signal, again, this is just the bin number. So we see 0, 1, 2, 3. And so the frequency information for all this data is going to be the fundamental frequency of our FFT multiplied by this bin number. Okay, so let's look at how the FFT is figuring out the level of energy for the signal throughout the spectrum. And I'm going to do this using the signal that we recorded earlier in the lecture where we were reconstructing a square wave. This is the version of it that we recorded with just the first 3 harmonics, and we set it to this really specific fundamental frequency of 86.1 cycles per second. So it looks like this in Audacity, and I've trimmed it so that the sound file starts exactly at the beginning of this cycle. So back here in Max, I've got a buffer. I've set the size of this buffer to exactly 512 samples, which is the default size of an FFT. And let's load this trimmed version of our signal. You can see that the signal fits perfectly inside this window of time, which is 512 samples. So the way an FFT works is it's going to try to correlate the signal one window at a time. And that window is the size of the FFT. So by default, that's 512 samples. So it's going to do the analysis on blocks of the signal that are 512 samples at a time. And the analysis is going to be based upon comparing the signal to every sine wave that fits inside that time period perfectly. So here is the first sinusoid that perfectly fits inside that same amount of time, 512 samples. So let's compare these two. I'm going to use peak tilde to read out the amplitude values of these buffers. And let's actually demonstrate this by, let's fill this buffer with just constant values of 1. And I'm going to use thresh to take all those amplitudes and put them together into one big list. So there it is. There's our buffer that's full of 1s. Let's change it to a sine wave. So this is all of the amplitude values inside this buffer, which is a sine wave that repeats itself perfectly one time inside our FFT window. So that's that one, and this list is going to be this buffer. So here are all the amplitude values of this signal that we're going to be analyzing. So our analysis is going to be this versus this, plus every other sinusoid that perfectly fits inside this chunk of time, 512 samples. And the way we do this analysis is by multiplying together all these different amplitude values and then taking the sum of that multiplication, and so that is the product of these two signals. So let's try taking the product of this versus a buffer that's full of 1s. You can see the result is pretty close to 0. So this does not correlate very well to this, but let's do it again, trying to correlate this to this sinusoid. You can see we get this large non-zero value. So the product is some kind of measurement of the correlation, and that comes because here we're multiplying all these positive numbers by all these positive numbers. So that gives us a lot of large numbers. Here we're multiplying all these negative numbers by all these negative numbers. And that gives us more positive numbers because minus times minus equals positive. And then we sum it all together and we get this big value. That tells us there's some correlation here. Let's look at the next sine wave that fits perfectly in this window. Here is the sine wave that repeats itself 2 times in 512 samples. And let's take the product of this and this. It's pretty close to 0. And this is actually expected because we know that square waves only have odd numbered harmonics. And this is an even numbered harmonic. So our measurement here is close to 0. But let's compare it to a sine wave that repeats itself 3 times. Now we again have a large number. So that tells us we've got lots of energy here in this frequency bin, where this frequency bin is 3 times the fundamental frequency of the FFT. So the fourth one is going to be, again, close to 0 because there's no energy at the 4th harmonic. But the 5th harmonic, boom, we've got another high amplitude value. 6 is going to be close to 0. 7, you might expect something here. But remember, this was based on just the first 3 harmonics of the square wave. So there's actually nothing here. This would be the next odd numbered harmonic, and we didn't synthesize that. So everywhere else in the spectrum, we're going to continue to see these much lower, closer to 0 values, showing us that there's not much energy in that part of the frequency spectrum. So that's basically how the FFT works, is by comparing this chunk of our signal to every sine wave that perfectly fits inside the same window. And we know the frequencies of these sine waves because we know the sampling rate of our system. So our sampling rate is 44,100 samples per second. And we've got 512 samples in this window. So this window, the sine wave that fits perfectly inside it, repeats itself 86.1 times per second. So when our sampling rate is 44,100 and the FFT is 512, this is the fundamental frequency of the FFT. And then all the other bins are going to be just every integer multiple of this base frequency. And it's just going to go up and up and up throughout the spectrum. Now, let's remember that the spectrum that we can represent with this system is 1/2 of the sampling rate. So our sampling rate is set to 44,100 because we want to be able to describe signals that go up to 1/2 of that value, 22,050 cycles per second. That's the whole range of human hearing in terms of frequencies. So with a base frequency of 86.1, in a system that goes only up to 2,050 cycles per second, the number of frequency bins we can actually represent is 256, and that happens to be 1/2 of the FFT size. So our FFT size was 512. We divide it by 2, and that tells us how many frequency bins we're going to get as a result of the FFT. Word. Okay, one last thing I want to go over in this lecture is this equivalency relating the time domain and the frequency domain in terms of convolution. So we looked at convolution recently, and you can think of it as a sort of shifting function. So when we're modeling the acoustics of a space, we take an impulse response and we shift that impulse response signal throughout time. So that's convolution in the time domain. And it turns out that convolution in the time domain is equivalent to multiplication in the frequency domain. So in the frequency domain, when we're looking at a signal, we're looking at how much energy there is throughout the frequency spectrum. So we're going to take that level of energy and multiply it by the other signal when we're doing convolution in the time domain. Crazy. So, all right, let's put our impulse response into this convolution engine. Here's our impulse response from the forest.
Sound of my speaking voice. I am sitting in a room.
And in effect, what we're doing here is we're looking at the spectrum of the impulse response, the spectrum of our input signal, Alvin Lucier's voice, and we're multiplying those two spectrums together. So that's what we mean when we say the convolution in the time domain is equivalent to multiplication in the frequency domain. Okay, so to make this super clear, let's put a kind of experimental impulse response into this convolution engine. I've got a square wave here that fades out quickly. And we understand what the spectrum of this square wave is now. Let's listen to the convolution output. So it sounds like a little bit like a vocoder, like the robot voice. But we know it's actually doing something mathematically really specific. It's taking the spectrum of the square wave, where we've got the fundamental frequency and all these harmonics, and then we're taking the spectrum of our input sound, the human voice, and we're multiplying those two spectrums together to get this output. So convolution in the time domain is equivalent to multiplication in the frequency domain, and vice versa. So here we've got a couple oscilloscopes. Yes, you are. We know you're sitting in a room. All right, let's start off by just looking at what happens when we add together two different audio signals and plot them in the frequency domain. So on our y-axis, we've got magnitude or amplitude, this measurement of energy in the signal, and our x-axis is frequencies. So here we've got one sine wave, and we can see we could have this big peak exactly at 1000, the frequency of this signal. And if we add together the second signal, you just get these two signals, and you see them both in the frequency domain. You've got your 1000 cycles per second and your 5000 cycles per second. But when we multiply these two things together, and we're multiplying in the time domain, we get something totally different. So look at the plot of this. We have one signal at 1000 and one at 5000, but they're both gone. Instead, what we see is a peak here, this is 4000, and another peak here at 6000. So what we have is convolution in the frequency domain. In the frequency domain, this signal is shifted by this signal, and vice versa. So multiplication in the time domain is equivalent to convolution in the frequency domain, and convolution in the time domain is equivalent to multiplication in the frequency domain. All right, so go climb a mountain and meditate upon that concept. That's our lecture. We'll see you next time. Peace.